For our final talk in this special Kavli Symposium, we are thrilled to have a representative from the LIGO research team. As I'm sure everyone in this room knows, just a few weeks ago, there was a very exciting announcement of the detection of gravitational waves. This is something that gave chills to all physicists, and we're very fortunate to have Duncan Brown to represent LIGO and tell us the story of this exciting discovery. Duncan is the Charles Brightman Professor of Physics at Syracuse University. He earned his PhD from the University of Wisconsin-Milwaukee and held a joint appointment with the LIGO Laboratory and Theoretical Astrophysics groups at Caltech before joining the faculty at Syracuse. He's been a member of the LIGO Scientific Collaboration since 1999 and is a Research Corporation Cottrell Scholar, a Kavli Frontiers Fellow, and a Fellow of the APS. Please join me in welcoming Duncan Brown.
Okay, thank you, and thank you to the organizers for inviting me. I'm very happy to be here today to tell you about something completely different to what we've been hearing. This is the first direct discovery of gravitational waves by LIGO. This is something that has been many, many years in the making, and it's very exciting for all of us involved. There are many people who made this happen over a number of years. To be able to stand here and say, we detected gravitational waves, and we found black holes colliding into each other at about half the speed of light. So this is a thrilling discovery. So our story begins about 1.3 billion years ago. This is a simulation of two black holes going around each other. As the two black holes orbit around each other, they lose energy and angular momentum into gravitational waves. And so the black holes get closer and closer together. They orbit faster and faster until eventually they collide together, merge into a single black hole, and rings down. So what you're seeing here is a full computer simulation of that happening with all of the gravitational lensing from the black holes on a stellar background in the background. So things settle down to this final state. So that happened in our universe about 1.3 billion years ago. The gravitational waves generated in this collision have been traveling through the universe for the last 1.3 billion years until they finally passed through the Earth the day after we turned Advanced LIGO on, which was pretty nice. So let me spin forwards to the early 1900s. So in 1915, Einstein wrote down the field equations for general relativity. So we just passed the 100-year anniversary of general relativity. And then in 1916, he wrote down the equations that describe gravitational waves. So ripples in the curvature of space-time that propagate out at the speed of light that carry information about changing masses. Now, we know from electromagnetic theory that you can't have monopole radiation. You can't have conservation of charge forbids monopole radiation. And conservation of mass forbids monopole radiation in gravitational theory. Conservation of angular momentum forbids dipole radiation in gravity. So the lowest order radiation you can have is quadrupole radiation. So this is two massive objects orbiting around each other. And the information about those changing gravitational fields takes time to propagate out to the universe, and the carriers of this changing gravitational wave are the carriers of this changing information are these gravitational waves shown here on this cartoon. And I keep emphasizing this. The important thing is that these waves carry information about the sources that generate them. The goal of LIGO, the goal of gravitational wave astronomy, is not just to detect gravitational waves, but to use the waves that we detect to do fundamental physics and astrophysics, measuring the properties of the sources that generated them and exploring the nature of the universe through the gravitational waves that we observe. So what's the physical effect of a gravitational wave? How do we go about detecting them? Well, a gravitational wave stretches and squeezes the distance between objects. So after Einstein wrote down the field equations in 1915, and then the equations describing gravitational waves in 1916, there was a debate that lasted many years about whether or not gravitational waves were real, or it was just a coordinate effect in general relativity. And in 1957, at a conference in Chapel Hill, Felix Pirani realized that the physical effect of a gravitational wave is this tidal deformation, the stretching and squeezing of freely moving bodies that Feynman then generalized to the sticky bead argument. If you have, imagine two of these test particles being on a stick, sliding backwards and forwards, so the gravitational wave changes the distance between them. There's some friction, the stick heats up. That energy has to have come from somewhere. That energy comes from the gravitational waves. And Bondi formalized this, and after 1957, people realized that, yes, gravitational waves are a real physical effect. They're not just in the math of GR, and people went out and set about trying to build gravitational wave detectors. So that's when the field of gravitational wave astronomy started in earnest. And the challenge is that the strength of the gravitational waves is given by the strain, which is the change in length divided by the length. So my nice big ring of particles with a plus polarized gravitational wave traveling through the board, I have a strain, change in length over length, of order unity in this circle. So gravitational wave strains that we saw on the Earth were this big. They'd be easy to detect. They'd be kind of painful for us. So what are the typical strains from astrophysical sources arriving on the Earth? Gravity and matter couple much, much more weakly than electromagnetism and matter. It's very, very hard to generate detectable amounts of gravitational waves. You can't build a gravitational wave generator in the lab, build a gravitational wave receiver like people did back in the days when people were exploring the properties of the electromagnetic forces. So what you need to do is look for astrophysical objects, massive compact objects. You need to take many times the mass of the sun, pack it down into objects tens or hundreds of kilometers across. You need to get them moving around each other at significant fractions of the speed of light, so at half the speed of light, going all the way up to almost the speed of light. And you need these objects generating gravitational waves. They'll be at a large distance from the Earth, the astrophysical sources, and we need to try and receive these gravitational waves here on the Earth. Now, the strain from these astrophysical sources, if I put some numbers in, the strain H goes as g over c to the fourth, so the physical constants are working against us. That's a very small number. The non-spherical part of the kinetic energy, so the part of the kinetic energy that's in that quadrupolar motion, divided by some very large distance to an astrophysical source. And if you calculate this for typical sources, binary neutron star systems, so two 1.4 solar mass objects moving around each other, out at maybe 100 megaparsecs away, you end up with strains of order 10 to the minus 21. So these are very, very, very small strains, incredibly challenging to detect. But don't let anybody tell you that gravitational waves are weak. The coupling between gravity and matter is very weak, but the gravitational waves themselves, the energy radiated is enormous. The luminosity of the gravitational waves goes as c to the fifth over g, which is a big number. The velocity relative to the speed of light to the sixth power, and then the size of the system relative to the Schwarzschild radius to 1 over r squared. And so if you plug in typical numbers, you get 10 to the 59 ergs per second. So a huge amount of energy radiating gravitational waves. So compare that to solar luminosity of about 10 to the 33 ergs per second, or the most intense gamma ray bursts of about 10 to the 49 to 52 ergs per second, and you get a huge amount of energy radiated in gravitational wave events when black holes collide into each other. But because of this coupling, it makes it very hard to detect, and we're looking for strains of order 10 to the minus 21. So what's the experimental challenge of detecting a strain of order 10 to the minus 21? Well, to put some numbers on that, I have a cartoon that I show. So imagine that you want to measure the distance between the Earth and the nearest star outside our solar system, Proxima Centauri. That's a distance of about 4.2 light years. So it's 4.2 light years from us here on the Earth to Proxima Centauri. The challenge of measuring strains over kilometer scales on Earth of 10 to the minus 21 is equivalent to measuring that distance of 4.2 light years to a precision of 10 microns. So this is incredibly precision measurement that's required to detect these gravitational waves. So how do we go about doing it? Well, we start with something that people are probably familiar with from undergraduate lab, a Michelson Interferometer. It's a fairly simple setup. We take a laser, we shine a laser at a beam splitter. Half of the laser beam goes towards the mirror up here, half of the beam goes towards the mirror here, come back, recombine them at the photodetector, and if we align the mirrors properly, we can get constructive interference, so all the light goes back towards the laser, destructive interference down here, so no light goes towards the photodetector. And if something comes along that changes the distance between these mirrors, say a gravitational wave passes through the plane of this detector, stretching and squeezing the arms, then we can detect an interference pattern at the photodetector. And it's fairly easy to make a toy version of this using a few tens of dollars worth of optics and a laser pointer, and you can bang on the table, you can see the mirrors vibrate, and you can see an interference pattern. But that doesn't get you to strains of order 10 to the minus 21, 10 to the minus 22 to detect astrophysical gravitational waves. That began in 1972 when Ray Weiss wrote down the design study for the first interferometric gravitational wave detector. So taking the simple Michelson experiment and scaling it to the sensitivity detector that could actually find gravitational waves. And if you ask, I want to make my gravitational wave detector sensitive enough to see these things, first question you might ask is, how long should the arms be? And if you do the calculation, you want the light stored in the arm of the interferometer for about half a gravitational wave period. That way you get the biggest phase shift on the light as you get the stretching, and it doesn't get canceled out by the squeezing in the other half of the cycle. So then you can ask the theorists and say, well, if I have two neutron stars going around each other, or two black holes going around each other, at frequencies that I can maybe hope to detect on Earth, so frequencies higher than seismic noise, that I can isolate this interferometer from vibrations, that limits me to about frequencies above 10 hertz, what type of frequencies am I looking at? And you realize that you get frequencies around 100 hertz. We're looking for gravitational waves around 100 hertz. Do the calculation, and you realize you want an arm length of about 1,000 kilometers. Now, that's not really practical. So what you can do, and this was proposed by Ron Drever and Ray and others, is to actually bounce the light backwards and forwards between the two mirrors many, many times, in fact, about 200 times, 300 times in advanced LIGO, and give it an effective arm length with a Fabry-Perot cavity. So you store the light in the arm for 300 bounces, and then you can build something that's maybe 4 kilometers long, but has an effective arm length getting up into hundreds and thousands of kilometers. So that's what we do. We have the Michelson Interferometer. We scale it up. We have lots and lots of servo systems to control the laser frequency, to control the amplitude of the laser, the frequency of the laser, the length of the arms. In fact, the job of a LIGO detector is actually to fight the response of gravitational waves and try and keep the interferometer resonant, try and keep the light resonant in the arms, so it actually acts to fight the effect of the gravitational waves above the unity gain frequency. And as the light bounces backwards and forwards between these arms, you build up gravitational wave phase shift. So this is Weiss's design from 1972, and this is what the current detectors look like. This is the advanced LIGO detector. So LIGO has a long experimental history, beginning in 1972. The project started in the early 80s as a project to really try and build a kilometer-scale gravitational wave detector. We built a 40-meter prototype at Caltech. That was used to develop the technologies that would ultimately go into the advanced LIGO, into the LIGO detectors. Then we built the initial generation of LIGO detectors. Construction of initial LIGO started in the mid-90s. The LIGO detectors turned online around 2000, and the initial LIGO detectors ran from over about a 10-year period from 2001 to 2010, running at a sensitivity where it's possible but not probable that we would detect gravitational waves. But they blazed the trail for proving to people that we could build and operate kilometer-scale gravitational wave detectors that could get down to strain sensitivities about 10 to the minus 19, 10 to the minus 20. In parallel to the operation of initial LIGO, the first generation detectors, we began to design advanced LIGO, the generation of gravitational wave detectors where we expected to get down to sensitivities where we could really detect astrophysical sources of gravitational waves. And this is a picture of advanced LIGO. It's kind of like the Michelson Interferometer, but it has a few enhancements to it. So first of all, here's the laser in the corner here. The laser shines light. This is the laser shines light through this mirror here onto a beam splitter, and test mass here, and test mass here. So that would be the simple Michelson Interferometer. What we do is we bounce the light backwards and forwards in these Fabry-Perot storage cavities. That gives the interferometer a longer effective arm length. And then the light that gets reflected back towards the laser, we put a power recycling mirror here to shine that light back into the detector and make it look like we have a more powerful laser. So we have more powerful laser light coming in here. And then we have another trick just in front of the photodetector called a signal recycling mirror. You remember I said you want to store the light for half a gravitational wave cycle? Well, if the sidebands on the light carrying the gravitational information hit the signal recycling mirror, they get reflected back into the detector, you flip the phase, and you can build up phase shift from the other half of the gravitational wave cycle. So you can get better sensitivity to this signal recycling mirror. It also lets us do some tricks in the future that will let us shape the noise curve and maybe look for more sensitivity around specific frequencies. So it gives a lot of flexibility. So this is the design of the advanced LIGO detectors. What's not shown here, this is just the optical layout. What's not shown here are the isolation stacks. We have two layers of active isolation as well as the passive isolation of suspended pendula. We have many control servos that control the length of the arms, keep everything resonant, keep everything locked. And that together makes up the advanced LIGO detectors. We have two of them, one in Hanford in Washington State, one in Louisiana in Livingston. What's shown on the right-hand side here is the design noise curve for the advanced LIGO detector. And the x-axis here shows the gravitational wave frequency. The y-axis shows the amplitude spectral density of the strain. And the colored lines show the contribution of different noise sources to the detector sensitivity. So at very low frequencies, we're limited by seismic noise. So as much as we try, we can't perfectly isolate the detector from the ground. So we're limited seismic noise below here. In the middle, we're limited by thermal noise of the optical coatings on the mirrors. So this is KT noise. This is thermal noise on the mirrors. Here, we're limited by at lower frequencies and higher frequencies, we're limited by quantum noise sources. So here it's photon shot noise. The counting statistics of LIGO is a timing experiment. We're using the phase fronts of light to measure how long it takes the light to go down one arm and back relative to the other. And we're doing that by counting photons at the photodetector. So that gives us shot noise here. If you turn up the laser power, you can make that better. But here we're limited by radiation pressure. The light is pushing on those mirrors and giving us a noise source on the mirrors. And so you turn up the power here, and the noise actually goes up here as the radiation pressure gets worse. So mostly across the range, we're actually limited by quantum sources. So we built this. This is what it looks like inside. This is one of those suspended, the quad suspensions. We have the test mass on the bottom here, a couple of the LIGO scientists for scale. We have a test mass here. This is the thing that will react to the gravitational wave passing through the detector and measure the signal that we're looking for. And this is the passive seismic isolation, the active seismic isolation, and then we have control systems that can control the positions of the mirrors to keep everything locked and resonant. This is what it looks like from outside. This is the LIGO Hanford detector, 4-kilometer long arms with the corner station in the middle, with the laser and the beam splitter and the photodetector in the middle, and then the end test masses at the end here. So we built Advanced LIGO. Advanced LIGO was a 5-year project. We ripped everything out of the initial LIGO detectors, save for the beam tubes and the vacuum, installed completely new systems, lasers, isolation, optical topology. Everything was new. And we expected to have a period of commissioning where we turned the detector on. It turned on with better sensitivity than initial LIGO when we first turned on, but just better. We had about 6 months, 8 months of commissioning the detectors, making the sensitivity better. And we expected maybe a 2 or 3 year period where we would gradually get the detectors down to the expected strain sensitivity, that design curve I just showed you, and then be in an era where we're detecting gravitational waves. So this is where we turned on in mid-September. This, again, is a noise curve, so gravitational wave frequency on the x-axis, and then strain amplitude spectral density on the y-axis. The white curve shows the noise sensitivity of initial LIGO. So we're most sensitive here in the noise is lowest here in the couple of hundred hertz region, so that's where we have the most sensitivity. That's what we achieved, the best sensitivity we achieved in the initial LIGO run. And this white curve down here shows the advanced LIGO design sensitivity from the previous slide, what we're expecting given the design of the detectors, the components we have, where we thought we'd be getting down to in around 2017, 2018. And the two curves, the blue curve and the orange curve here, show the sensitivity when we turned on in early September. So we have somewhere a factor of 3 better than initial LIGO, and maybe a factor of 3 away from advanced LIGO. So better than we left off with initial LIGO, but not quite at the full design sensitivity. So like I say, we expected to settle in for interleave commissioning observing periods where we'd observe for a while, improve the detector sensitivity, observe for a while, improve the detector sensitivity, and then get to the point where we're detecting gravitational waves. And then what happened was, on September 14th, right after we finished the calibration, we saw that. So this is the signal of two binary black holes colliding into each other. So what's shown on the x-axis here is the time in seconds. What's shown on the y-axis is the frequency. So this overlays two things. The trace here in orange is the strain signal coming out of the gravitational wave detector. So the calibrated strain signal coming out of the gravitational wave detector. For the Hanford detector on top in orange and the Livingston detector beneath in blue. And we've done a little bit of band passing. We've just run it through a graphic equalizer. We've suppressed the low frequencies where things are very noisy. We've suppressed the high frequencies where things are very noisy. And we've added a couple of line filters to get rid of some violin modes of the suspension wires. But that's it. We just run it through a digital filter that looks like running it through a graphic equalizer. And you can see this beautiful, clear signal in here with these cycles and then going back to the noise level right here. You can see the signal in the data with very, very, very minimal filtering. What's shown on top is a time frequency spectrogram of the signal. So this is the gravitational wave frequency from 32 to 512 hertz. And you see it sweep upwards in frequency. The color shows the amplitude of the signal. So you can see both sweeping upwards in frequency and amplitude. And this is exactly characteristic of what we'd expect from the chirp signal of two compact objects in the last few moments of orbit, merger, and then ring down to a final compact object at the end. So let me play this a couple more times for you, if we can get the sound. I guess we don't have the sound. Well, what you can hear is you can hear the rumble of the detector data, and then a nice whoop at the end. You can hear the signal in the data. You just hear whoop in both detectors with very, very, very minimal filtering. You can see the signal in the data. You can hear the signal in the data. This is absolutely, absolutely beautiful. I did not expect this. Okay, so this is GW150914. This is a gravitational wave signal observed September 14th, 2015 at 9:50:45 UTC. It arrived first at the Livingston detector, and then 7 milliseconds later it arrived at the Hanford detector. So the travel time between the detectors is less than the maximum light travel time between the sites. So this is all consistent with what we expect, that the propagation speed of the gravitational wave should be the speed of light. What's shown here is, again, the Hanford signal, the Livingston signal, and then if you take the Hanford and Livingston data and you shift them by that 7 milliseconds to line them up, and then Hanford and Livingston actually have different alignments. You have to flip the phase of the Hanford signal, which you expect because the Hanford and Livingston detectors on the surface of the Earth are 90 degrees to each other. So you account for the distance between the sites, you account for the orientation of the sites, you plot the two signals on top of each other, and you see this beautiful coincident chirp, inspiral merger, ring down signal in the data. And you can ask, what is this? What have we seen? And the signal is so loud, you can just look at the data and do some back-of-the-envelope calculations from senior level relativity class and figure out what it is we see. You can count the cycles, and you can see that over 0.2 seconds, the signal increases in frequency amplitude in about 8 cycles from 35 hertz to a peak amplitude around 150 hertz. That's the amplitude of the peak right here. And you can say, what is that? Well, what you can do is you can take the classic Peters and Matthews calculation that does nothing more than take Newtonian mechanics, say, okay, I have two objects orbiting around each other in Newtonian mechanics. They have a kinetic energy and a gravitational potential energy from the orbit. And I can take the Einstein quadrupole formula that says I'm losing energy according to the third time derivative of the quadrupole moment. I can put that together and ask, as this system loses energy, how does the frequency of the gravitational waves evolve just at leading order from the Einstein quadrupole formula, from the Peters and Matthews calculation. And you find that at leading order, the frequency evolution is governed by this quantity called the Chirp Mass, which is the individual masses of the two objects, m1 times m2 to the 3/5, divided by the total mass to the 1/5 power. And so this is the Chirp Mass. This is the thing it's easiest to measure from gravitational waves. And it's given by this formula from the Peters and Matthews calculation. And you can say, well, I've measured F and I've measured F dot, so what's the Chirp Mass? I can just read F and F dot off approximately from the figure I just showed you. And from this, you can bound the Chirp Mass, and hence you can bound the total, you can measure the Chirp Mass, and so you can bound the total mass to, these two things have to be bigger than 70 solar masses. And you've got two compact objects that are bigger than, where their total mass is bigger than 70 solar masses, and you can see them inspiraling at a frequency, orbital frequency of 75 hertz. The orbital frequency is half the gravitational wave frequency. So you've got to have two objects with at least a total mass of 70 solar masses that is still going around each other without contacting each other at an orbital frequency of 75 hertz, going around each other 75 times a second. And the only objects that are compact enough to do this without touching are black holes. So this is very good evidence, just from looking at the data, doing no fancy signal processing, just cycle counting the data, that we've seen two black holes orbiting around each other, colliding and merging. You might ask, oh, well, what about a black hole and a neutron star? Are they compact enough? Well, to get a chirp mass matching the inspiral evolution, you'd have to have a 3,000 solar mass black hole and a 1.4 solar mass neutron star, and they would merge before 70 hertz. So that rules out black hole neutron star, and neutron star is ruled out by the mass constraints. So this is very good evidence this is a binary black hole merger, just without doing any fancy signal processing. So let's do some fancy signal processing to measure how significant the signal is. What we do is we match filter the data using a bank of waveforms generated from relativity. So we solve the equations of general relativity either numerically on a computer or analytically as best we can, and we get a bank of waveforms that cover a big space of compact objects from neutron stars in one corner to high mass black holes in the other corner, and we search the data completely blind for these signals. And this is our match filter search. And we did this over data taken between September 12th and October 20th to have some nice long period of data to measure the instrumental behavior over a large period of time. We measure the noise background over this period of time by reanalyzing data, introducing an artificial time shift. So we take the data from the detectors, we shift it by more than the light travel time. That effectively turns off signals, and we say what's left, and what's left is just noise. We repeat that many, many, many times so we can get a measure of noise background of our search relative to the search with noise and signals in when we just analyze the data without any time shift. And when we do that, when we measure the detection statistic here is the match filter signal to noise. This is the number of events. What this plot shows is the result of the search. So we have this signal way out here at a combined match filter signal to noise ratio of about 23. Very, very, very loud. And these curves here show the noise background of the search. And this thing is so far above the noise background. There are two curves on here. The black curve, the signal is so loud, when you time shift the data, the individual pieces of the signal line up with random noise in both detectors and give you a noise signal background that is this tail extending out here. So this is actually coincidences of the signal itself with noise in the other detector when we do those time shifts. But it's louder than even combining itself with the loudest piece of noise from the other detector. When you remove the signal from the data and you say, what's the noise background without GW1509 in there, 150914 in there, you get this purple curve. And that's the noise background in the detector without the purple curve. So even without doing that, it's much greater than 5.1 sigma. When you look at the noise background without the signal in there, it's way, 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 way much greater than 5.1 sigma. This is a false alarm rate of about 1 in 203,000 years. And the only thing that stopped us is the fact we wanted to publish the paper at some point, and that's why we stopped this analysis here. The observing run is still ongoing. We observed until the middle of January to take the data. So we are absolutely confident, not just from looking at the data, which is a great, we're doing an experiment. If you can see the result of your experiment directly in the data without doing anything fancy, that's fantastic. Doing the full statistical analysis shows that this is a much greater than 5.1 sigma detection, very significant signal. Then we can ask, what have we seen? now we can do Bayesian parameter estimation coherently between the detectors to measure the signal that we've seen in the detector data. And from that, we can get the primary mass, the mass of the larger black hole, is about 36 solar masses. The secondary mass is about 29 solar masses. Its luminosity distance is 410 megaparsecs, corresponding to a redshift of almost 0.1. And then the final black hole mass that was formed in the merger is about 62 solar masses, and the spin of the final black hole is about 0.7. So we can do this fancy parameter estimation, and we can feed that back into numerical modeling, and we can actually get our friends in the numerical relativity community to simulate that signal. So this isn't a cartoon of gravitational waves. This is a full general relativistic numerical solution of the Einstein equations for that signal that we measured. And so you can see the two black holes orbiting around each other. The green shows the gravitational waves radiated away. So as the two black holes get closer and closer together, they orbit faster and faster. The strength of the gravitational waves increases until eventually they merge into a single black hole, ring down, and that's the burst of gravitational waves that's been traveling through the universe for 1.3 billion years, arriving here on September 14th last year. And from this numerical simulation, we can fit to how much mass has been lost in that inspiral. In the waves that we detected, radiated in the inspiral, that system lost 3 solar masses in gravitational waves. It radiated away 3 m sun c squared of energy in gravitational waves. That's a huge amount of energy. In the merger, the energy radiated is about 10 to the 56 ergs per second. To put that in solar masses, in m sun c squared, that's about 200 solar masses per second of energy radiated away in that collision. These two black holes collide into each other at half the speed of light. That is an incredible amount of energy. That outshines all the stars in the universe. So, we have detected gravitational waves from a binary black hole merger. We've proved gravitational waves, that we can measure the amplitude and phase of gravitational waves. We can directly detect them. We've proved that these binary black hole mergers exist. That's just the beginning. Now we can start to do some cool fundamental physics and astrophysics. It's the best test for general relativity in the strong field nonlinear regime. And we can start to do tests bounding the mass of the graviton from the dispersion relation on gravitational waves. And we can put bounds better than the solar system or pulsar bounds, not quite as good as some of the model-dependent weak lensing bounds, but direct bounds that are independent of assumptions. We can bound the Compton wavelength of the graviton, equivalent to bounding the mass of the graviton, and we can start to do these strong field tests of general relativity. With this merger, we find no evidence for disagreement with general relativity. The detection of these binary black holes has implications for massive star formation, for our understanding of how stars live and die. The universe is really good at blowing up stars. We're really bad at understanding how the universe does that. We don't understand the supernova mechanism yet. So we don't understand how stars live, die. We don't have a complete picture. So detecting these gravitational wave sources, this has already given something completely new. Black holes larger than 25 solar masses exist. This is the first observation that black holes as massive as this in the stellar regime, before you get to the massive black holes at the center of galaxies, actually exist. Binary black holes exist and merge within a Hubble time. These alone have implications for stellar wind physics, understanding the evolution of massive stars. We know that in order to reach 25 solar masses, these black holes must have formed from stars in a relatively low metallicity environment. So you have relatively low stellar winds. You don't have a lot of mass loss. So you can have black holes forming. There are different mechanisms. So these formed in dense clusters. They field binaries. We're exploring the different mechanisms of black hole and binary black hole formation, massive star formation, common envelope phase, lots of uncertain physics and astrophysics that we can begin to explore with these gravitational, even with a single gravitational observation. We can start to ask, where did the source come from on the sky? This is the localization. With 2 detectors, you get a ring on the sky. You're doing localization by timing. You get a ring on the sky. Some of the degeneracy of the ring is broken by the relative amplitudes and looking at the relative amplitudes of the signal in the 2 detectors, but you don't get great localization with a 2-detector network. But people have followed this up with electromagnetic facilities to look for any possible counterparts to signals. And that's going to be very exciting moving forwards, particularly as we start to detect binary neutron stars maybe next year, or maybe relatively soon, we'll detect binary neutron stars. So as two neutron stars crash into each other, you can get a very large flash of radiation, perhaps a gamma ray burst, perhaps a kilonova, the R-process decay of the neutron-rich material that's thrown off as these two neutron stars merge into each other. Perhaps that neutron star merger is the source of the gold and platinum in the universe. And with the network of gravitational wave detectors, so with LIGO Hanford, Virgo that's under construction, Kaga in Japan that's under construction, and LIGO India that's been given the green light by the Indian government, we'll have a worldwide network of gravitational wave detectors where we can get precise sky localizations and say, we saw a gravitational wave source, point your telescope there and tell us if you saw an electromagnetic counterpart. In the gamma rays, in the infrared for the kilonova, in visible light, a whole slew in X-rays, a whole slew of multi-messenger astronomy to explore the universe with in an entirely new way. So this is a very, very exciting time for physics and astrophysics. LIGO has made the first measurement of gravitational wave amplitude and phase. Merging binary black hole system has been seen for the very first time. We have more data in the can. We have 2 months more data in the can that we're analyzing right now and hope to have results soon. And LIGO is coming back online in late summer, fall of 2016 with improved sensitivity as we've done more commissioning. Virgo will join in, so we'll have a 3-detector network and be able to do better sky localization. And I think it's fair to say the next few years will be very, very, very interesting ones for the field of gravitational wave science and the wider community of physics, astrophysics, and astronomy. We're at the beginning of a whole new field of gravitational wave astronomy, and that is a very, very exciting place to be. So with that, I'd like to close and say, it takes a village to raise a child. It took a lot of people to make this happen. The LIGO scientific collaboration, together with the Virgo collaboration, over many, many years. I've been doing this for 17 years of my life, and I'm not even by anywhere close to being some of the oldest in our collaboration. We have everyone from undergrads who've been in a year who joined my group, and they said, oh, yeah, you might detect something, and then they're writing their senior thesis on the detection of gravitational waves, through people like Ray and Ron Drever and Kip, who've been doing this for more than 30 years. Josh Goldberg is an emeritus professor in my department. He's one of the people who organized the Chapel Hill Conference going back to 1957. A lot of people made this happen. These are some of the institutions involved. And of course, the vision of the NSF, who made this all possible by having the foresight to fund a research program that took 30 years to pay off, but has paid off in a really big way. So I'd like to stop there and take any questions. Thank you.
Who's proud to be a physicist right now? Raise your hand. Booyah. We have time for some questions right here.
So far, you detected a single event. There was no repetition. So my question is, how large is our universe? How many binary black holes are there? How often are they expected to collide? And when will be the second similar event?
Can you put the screen back on for me? So this is the search result. So this is GW150914 right here. And this is a 2 sigma thing right here. That 2 sigma thing right there, if you look at the PRL, it quacks like a duck, right? It's not significant enough to claim as a detection. Its false alarm rate is 1 in 2 years. So it's not the much bigger than 1 in 200,000 years that we've got over here. But don't dismiss this little guy here. Parameter estimation, it looks like a binary black hole merger. This is reported in one of the 13 companion papers to the PRL for this signal. So if you ask me, this little guy right here looks a lot like a weak binary black hole merger. So I think we're starting to see not just loud detections, but maybe beginning hints of a population. When are we going to, we have another 2 months of data in the can. The rates for binary black holes there's a companion paper that talks about the rates. The rates predicted in the companion paper are at the very high end of what people initially back of the envelope when we're looking at the rates. We have projections for O2 sensitivity, which is the run. And by the end of O2, if everything goes well, the rates paper projects that with almost certainty, given the measured rate from this one and this one right here, that we should have seen about 5 events by the end of O2, by the end of this year. So hopefully we won't have to wait too, if the rate is consistent with what we've seen, we won't have to wait too long to actually start seeing more signals and really be doing gravitational wave astronomy regularly.
Sir, you have the last question.
Gravitational waves are supposed to be quadrupolar radiation. Can you show this experimentally?
Yes. So what we can do is we can look for deviations from the predictions of general relativity, and we do this in all kinds of ways. So it's what we can do is we can basically say, okay, relativity predicts a certain amplitude and phase evolution for these gravitational waves. If you make modifications, these so-called post-Einstein modifications to general relativity, you change the amplitude and phase evolution of the gravitational waves, and so we can compare that to the observed amplitude and phase evolution that we see in these waves. What we've seen so far is completely consistent with the prediction of quadrupolar gravitational waves produced by two black holes of general relativity. We don't have any evidence for deviation from what we expected from Einstein. What we can't do yet, because this signal is not quite loud enough, and don't forget, we have another factor of 3 in sensitivity to go, so we're not at the bottom of our sensitivity well yet, even with advanced LIGO. What we'd really like to do is that ringdown signal, the ringdown modes. So the no-hair theorem says that all the modes of the ringdown signal are determined just by the mass and spin of the black hole. So if we can measure modes of the ringdown, we can actually not just say we think we're seeing objects that are compact enough to be black holes, they're emitting quadrupolar gravitational waves. We can say, have we seen a Kerr black hole of general relativity by looking at the mode content of that ringdown structure at the end. We're not quite there with this signal yet, but it's getting closer, much closer than I thought we would be in 2016. But everything right now looks consistent with GR.
Thank you.
Thank you very much. Thank you to all 5 Kavli lecturers for phenomenal talks. And thank you all for coming.